So, polar covalent bond. Remember when I mentioned that bonding is on spectrum, from one end to the other end, from ionic to covalent. On the opposite sides, in the middle, you have various kinds of bonding, and all of that is called the polar covalent bond. Because while you have ionic bonding on one side and covalent bonding on the other side, the bonding characteristics for all the bonds in the center would then be going from being less ionic and less ionic ultimately to covalent, pure covalent. So when does this polar covalent bonding happen? Well, it happens when electrons are shared unequally. Let's look at an example and it will become very clear. So here you have hydrogen and fluorine. Previously we saw how two hydrogens bond with each other to form a covalent bond, to form diatomic hydrogen gas. Then we also saw how two fluorines bond with each other to form the diatomic fluorine gas. But what if you have a hydrogen and a fluorine? Both of them can share one electron the way you see here. But these two electrons are not shared equally. The only way they are shared equally if they were both identical atoms. But they are not identical, they are different. They have different properties. For example, hydrogen has comparatively low ionization energy. Fluorine has much higher ionization energy. Hydrogen has low electron affinity. Fluorine has much higher electron affinity. So ultimately a new property emerges, which we'll talk about in a minute. But fluorine is said to pull the electrons closer to itself, keeping it for itself longer than hydrogen can. And so on average, fluorine carries a negative charge. Why would it be negative? Because fluorine not only has its own electron but an extra electron now, and it acts as if it belongs to it for a considerable period of time. Not forever, because ultimately they are shared. So if those two electrons belong to fluorine, fluorine would have a 1 minus charge because this one would be an extra electron. And hydrogen would end up with a 1 plus charge because it lost an electron. However, because it's not exactly gain of 1 electron for fluorine and loss of 1 electron for hydrogen, it's less than that. Regardless, it's unequal sharing, and we say that there is a delta. This symbol here is a Greek symbol called delta. There is a delta minus charge. Delta means somewhat. Okay? Somewhat minus charge, somewhat negative charge on fluorine, and there is somewhat positive charge on hydrogen. Can we calculate how much charge there is? Yes, we can, but in our course we are not going to do that. It's going to be less than plus 1 and minus 1 on each, some number between 0 and 1. Regardless, this is the unequal sharing of electrons, and the bond between them, although it's a covalent bond, it's not a fully pure covalent bond. It's called a polar covalent bond. Polar meaning there is now a polarity. What's a pole? Well, we have North Pole, one extreme, and South Pole, the other extreme on our planet. In terms of polarities for molecules, we are talking about charge polarities, a negative polarity on one end and a positive polarity on the other hand. So this is called a polar covalent bond. And there is a measure of how much of a polar covalent bond a bond will be, and that measure is electronegativity. Electronegativity is a measure of the ability of an atom to attract electrons in a chemical bond. This is different from electron affinity, which is just love for electrons and how much energy is released when electrons are gained by an atom with high electron affinity. Electronegativity specifically has to do with shared electrons and how much are they loved by each atom that are sharing those electrons. Electronegativity values allow us to figure out the extent of bond polarity between two atoms. An atom with high electronegativity will demand greater electron share for itself, and it will have the delta minus charge on it. And an atom with low electronegativity will not demand such an electron share for itself, and it will have a charge of delta plus on it. Here we have a table of electronegativities. And if you go across this table, there is one element with very high electronegativity, and that's fluorine. Fluorine is the most electronegative element of them all, followed by oxygen. And then you have nitrogen and chlorine. Those are the elements with 3.0 or above electronegativity. Then you have this elements here with electronegativities between 1 and 3. And finally, less than 1 are these metals here. So the most electronegative elements are found in the upper right corner, and the least electronegative are found in the lower left corner. Electronegativity trend is also similar to other trends. Electronegativity values increase from left to right, and they decrease from top to bottom. So left to right they increase, they decrease from top to bottom, making this top right portion the most electronegative elements being there. So how exactly can we use the electronegativity chart to figure out the polarity of a bond? Well, let's compare the hydrogen and fluorine bond with the hydrogen and chlorine bond. If you look in the table for the electronegativity values of the two elements, fluorine and chlorine, fluorine is 4.0, chlorine is 3.0, hydrogen is 2.1. Keep this in mind, and let's go and look at the bond. Now, we went a bit further. Now, in hydrogen and fluorine, the difference between the electronegativities of fluorine and hydrogen is 1.9, while the difference in the electronegativity of chlorine and hydrogen is 0.9. A more polar bond will have a greater difference in the electronegativity values, making the HF bond more polar than the HCl bond. And that's where we will stop our discussion of electronegativities. But I would like to mention this, that we do not do this exercise of finding the electronegativity differences just for absolutely no good reason. There is a reason. The electronegativity differences have of effects on the physical properties of compounds, properties such as boiling points, melting points, and their solubilities. We will briefly look at some of that in a later video.